Yeah, woo, we're streaming. All right, I'm gonna get my computer moved over here. I'm gonna have this focus on this whiteboard, so hopefully it can be seen. And we should be. I'm only gonna use that whiteboard. So that's what we're doing. I also need to get on my stream on this computer so that
Is it streaming right now?
Yes, it's streaming right now.
Can I say
So
something?
that I'm able to read any questions people have as we
Hey guys.
as we are going.
Mom, I'm on TV.
I'm gonna say that. Go right into the mic. Good job. That's the problem. The police are gonna find me. What's going on?
Oh no!
You're on a live stream. Watch out.
Oh
Anything you say will be called against you. Live stream.
Okay, well I should still be able to see the live chat. So I guess that's as good as it's gonna get.
Session or what? Yeah.
So, I will see. I don't know what the deal is.
Mr. Dielentheis, did you put like the answers to that one question on my
I did.
Number 4 is C.
Nikki, do you know the way? Do you know the way? Do you know the way?
Okay, so we are live. So let's get cracking. What do we want to start with?
Sure.
Projectile
Why don't we
motion.
start from the beginning of the year?
Kinematics.
Projectile motion. Yeah. Just go through each unit, do the what we should know, like a crash course in each
I
unit.
don't even know why I'm in here.
I don't even remember.
All right. So you guys how late do you want to be here?
Well, no. We could do some today.
The problem
Someone
is, I don't
Friday.
even remember the first unit, so I don't remember what I don't remember. If you just kind of like say it and then maybe like,
I
these
don't
are the
remember
main
what I
things
don't
you should have
remember.
got, and then if I have a question, you can be like, oh, I don't remember that.
That's not. But that puts the onus of responsibility on me to make sure that I'm covering the things that you need. And the purpose of this is for me to be a resource for you to be asking questions, not for me to say, these are the things you need to know. So I can do like a very, very basic outline, but I mean, I'm not going to spend more than 5 minutes per unit just to give you...
Like, write the list of units we did in order.
Yeah, I think I posted this on Power School as well, but I can be a little bit more in depth in that. Yeah.
So basically, it's like our review night, just like going over like doing problem questions. Or
You ask a question, I will answer it. Whether it's you want to go over a question in the book, whether you want a concept clarified, whether you want like something, you want something recovered or retaught, or...
Can we go over projectile motion again? I completely forgot what happened.
Sure. So before we do that, let's start out with what Ella was asking, and I do want to really quickly give you an overview of everything we've done over the past 4 months. And it's going to seem really depressing.
I'm pretty depressing.
What is it? Not a lot.
Yeah, because in 4 months, we've covered like 4 things.
We are aware.
So we start with kinematics.
What exactly?
What is kinematics?
Oh, no.
Okay.
Oh.
So,
I'm the past time.
I don't get this. It's telling me that there's an error.
Hey guys, wrestling meet at 6 o'clock. Come watch it, guys.
No.
I won't be wrestling since I got injured, but just come watch it anyways. Thank you.
Oh yeah, Nikki, we have to go see Brandon wrestle.
I'd rather watch
Do I
golf
really
than
want to go
wrestling.
see Brandon wrestle?
Yeah, because he lost 3 pounds for this match.
Oh yeah, you're
Yeah,
right.
we worked hard for it.
Whatever. Okay, so we start with kinematics. The important things in kinematics are going to be stack of graphs,
I'm gonna be watching with fourth band.
and the important things from stack of graphs,
Basketball movie. Yeah.
slopes and areas.
Derivatives.
Right.
No, we don't use those words. Say it again and you're out. I said derivatives. We don't talk about derivatives. We don't talk about integrals. It's not our jam. We talk about slopes and areas. The reason we use slopes and areas is because that's nice. That's nice. It's things we already understand. The second thing out of kinematics that I'll suggest you
Honestly, I'm only here for the
make
push.
sure you are aware of is projectile motion. 2D basically means something has an X and a Y component.
Oh, yeah.
Did we ever do 3D?
No.
I don't remember.
No.
We talked about it, but we never did.
Yeah.
You don't want to do three-dimensional motion.
How would that even work?
Well, so basically the only thing that would change in the real world, we have an X, Y, and Z, right? X, Y, Z. So in the X and Z direction, things don't accelerate anyways. So you still only have linear motion in X and Z. But in the Y direction, that's where you have your acceleration. So you would basically be doing the same thing,
What if
except
a slanty boomerang that would have projectile motion in 3 dimensions?
yeah, so the way you would do that, and I really don't want to get into this, but the
like,
way you would
just
approach,
what would be like, not how you would solve it, just what would be an example of 3D projectile motion?
well, I mean, if I threw this at an angle this way, you could say that that's three-dimensional. I could reorient my axes for that to be two-dimensional motion.
Okay.
But, I mean, anything in the real world could be considered three-dimensional motion, depending on how you're orienting your axes. Basically, it gets ugly because instead of getting to use, like, here's your X and Y, instead you have to worry, yeah, okay, good. I did not, oh, that was going to open a Pandora's box, and I did not want to do that.
What?
Okay, so in kinematics, stack of graphs, projectile motion, I really think those are the highlights there that are new from this year. Stack of graphs, really, you even should have done last year a little bit, but we really kind of, we finessed that a little bit. I required you to be a little bit above and beyond, you know, the slope of a Pearson time graph is your velocity. I wanted you to be able to do a little bit more. After kinematics, we went into momentum. And really the big new thing in momentum was 2D and glancing collisions.
What's the equation for momentum? Like
P equals mv. P being a vector, v being a vector.
Oh, then can you go over like the energy conserved, elastic, total? What are the differences between the two?
Yeah, so we have two types of collisions. Elastic with an A, and inelastic. In an elastic collision, kinetic energy is conserved. And that basically is going to mean, generally speaking, 100% of the kinetic energy from your first object is transferred into the second object.
That's a total elastic collision, right?
Yes.
What's the like not total one called? Like
Partially inelastic. Most collisions that we're going to deal with are, for the sake of mathematical ease, going to be either totally elastic or totally inelastic. When we do partially inelastic collisions, then that gets a little bit uglier. We can still do them, and that is generally how our glancing collisions are set up. So let me give you inelastic. Now kinetic energy is not conserved, but our bodies stick together.
Nice.
In both, momentum is conserved.
where does the energy go?
It's usually just dissipated energy.
Oh, okay.
We usually attribute it to sound, heat, friction. Like the big example that they give for inelastic collisions is you have like a lump of clay on a cart and a lump of clay on another cart, and you ram the cart into the other one, and the clay is going to stick together. And that energy loss is going to occur due to, you're going to hear something, and it's going to deform, literally deform the clay And so there's going to be some energy that gets transferred into the clay to deform it. That's where you have your energy loss. And then our partially inelastic is just Ke not conserved. And our masses don't necessarily stick together. The way we solve partially inelastic ones is we're going to have to be given a little bit more information about the system, but we know that our momentum is conserved. So when we do like a glancing collision, we might need to know the momentum of the second object, or the mass and velocity of our second object, or the angle at which it glances off at, or something. We have to know something about our resultant situation. Otherwise, we're going to have no idea because we don't know exactly how inelastic it is. And really, calling a collision elastic, inelastic, or partially inelastic, you don't really need those labels. It all just depends on the information they give you. So if they say the kinetic energy of the first body is transferred entirely into the second body, you don't need to know that that is an elastic collision. It is, but it's not like knowing the type is really going to help you. And since this is like an AP1 type thing, the AP exam, if it does wind up testing momentum at all, it'll very likely be like on the quest today where tension was included in there. So Newton's second law was sort of wrapped up into that problem from the quest today. But it's sort of like, it's not what the question itself is testing. Sort of getting at it a little bit, but not exactly 100%. So that's our two types of collisions, and that's what we need to get out of momentum. After momentum, we moved into energy. I'm going to change markers. This one is making me very sad.
I'm sad too.
So the big important things here are just conservation. And I think really the only things we did were, you know, having an object having a kid up on a slide. What's his speed at the bottom of the slide, assuming no energy, none of his potential energy is lost due to friction, right? It's a perfectly frictionless slide, or something like that, right? And those problems are usually pretty easy. The thing is you can apply energy conservation laws to a ton of different stuff. I mean, we could be looking at, we could do a problem with buoyancy and apply energy conservation to that sort of problem. So it's just like how they wrapped Newton's second into that buoyancy problem on the quest, where you have to find, the tension in that cable. It's not a quiz, it's not a test, it's a quest. Come on! I didn't even make that up. Like, that's a thing. It's a thing. It's a thing. Yeah. People backing me up.
Also, okay, friction. Did we do friction in any of those 3 units or no?
Friction, friction winds up being a form of dissipated energy.
Didn't we do something where we learned, like, mu and friction and stuff?
That was in forces. Yeah, I suppose we did forces before energy.
Okay.
Yeah, so I guess. So for forces, kind of the things that I would consider important here, friction is kind of important. I mean, you've got the equation on your equation sheet, and really the only time friction is going to be included, there might be a problem where they have you do something, and then all of a sudden they're going to say, okay, well now let's assume that there's friction. Redo the problem with friction. They might have a block falling down an incline, a curved incline like this, they might say, you know, find the speed of the block at the bottom of the incline. Okay, that's easy to do. Then they might say something like, okay, well then at the bottom of the incline they have a length of straight track that's sandpaper, or some rough surface with a coefficient of friction, you know, 0.6. How far does the block travel before it stops? And then you would have to be applying some force of friction, energy loss due to friction, work done by friction, that kind of stuff. So this friction then is sort of going to tie into the next unit, energy. And really energy is, like I had written up here before, pretty much just conservation law. Because I think calculating kinetic energy, calculating potential energy, calculating spring energy, these are things that are really not particularly difficult to do, assuming you're actually given the information, right? Like if I know M and I know how high an object is being lifted, I can get potential energy pretty quick. There's not a lot to be said there. From energy, we moved from, gosh, was it energy into rotational dynamics?
I think so.
I'm gonna say yes.
Yeah.
So I also want to say energy and work.
And work is something.
Work is force times distance.
Force times distance.
So it's not energy necessarily, but you know we talk about work done by different things. So like on this problem, it's the work done by friction. You could say the energy loss due to friction.
And we didn't do anything with like watts or anything.
No, we haven't yet.
Okay, good.
That will come into play more when we start talking about power. Well, we already sort of touched on power with energy and work. That's more important when we start getting into charged particles. Then we start talking about watts in terms of like lighting light bulbs and that kind of stuff. So there's that. After energy and work, then I think it was rotational dynamics.
Anyone craving some pizza right now? Nikki, you want some pizza? I don't. Oh, I'm waiting.
I just wanted to be on the live stream.
Honestly.
It's my dream.
What?
Live stream?
Yeah, I'm streaming it right
I
now.
wanted to be on the Twitch stream.
When I leave, I'm gonna watch it. Wait.
I can see if there are any people. Nope, nobody's watching.
No, wait. As soon as someone starts watching.
I'll watch it right now. Don't worry. I'm on it.
So rotational kinematics, we covered a lot of stuff here. Rotational kinematics, we also had our stack of graphs. We looked at the relationship between linear and rotational quantities. Really, I think the reason this takes a little bit of time is because you have to wrap your head around it. It wasn't really all that much new stuff. It's just that we don't, we spend the whole year in regular physics learning about how things move in straight lines. And then all of a sudden now I'm saying, okay, now we're talking about circles. And that's a bit of a leap mentally. But rotational kinematics, we're basically going to be doing stack of graphs and our relationship with linear kinematics.
Yeah, I don't know, like,
Hey, how do you do the live stream?
rotational kinematics was really hard. Like, that would be something, maybe after we finish what we did, going through, then we can do a practice problem.
Sure. Yeah, we can definitely do that.
Practice problem of each.
Yeah, that'd be good.
Okay. Well, what you'll need to do is you'll need to craft a question so that I can generate a practice problem, because like I said, I don't have anything. If you say, can we do a problem on kinematics? Okay, what about kinematics?
Projectile motion.
Question?
Can we look at old tests and give you the questions from these? Like if we got problems wrong, that way the questions come up quicker. If we
I have a good question. This one has been
Maybe.
on me for a long time. if you're on a merry-go-round and you're standing on the edge, which way is the friction force?
Frictional force is oriented inward.
Why?
Because there has to be a force keeping you on the merry-go-round.
But isn't your center seeking acceleration towards
That-
the center?
Yes, but that's because of your friction. Your friction is the force, the actual force, that is causing, so a centripetal force doesn't exist.
It's not a force.
It's not its own individual force. Just like net force isn't its own force, it just arises from other forces. So your center-seeking force has to be an actual force. Usually friction or tension. Those are your two centripetal forces. The forces that cause your center-seeking acceleration. Yeah. Good question, though. Good question.
What?
Every test is
No.
if you're on a merry-go-round, which way do you? Who was it that during one of our quizzes was like, "What's a merry-go-round?"
I think that was Rich.
He was like, "I think you need to pull up a video of a merry-go-round because I cannot picture what it is." I was like, Kyle, yeah. I swear he was.
So rotational kinematics. I'm gonna say stack of graphs and relation to linear. After rotational kinematics, then we plunge straight into torque. Yeah, torque being our rotational analog to force.
I can hear Emma back down from here. You can hear Emma.
Torque, the important things here are going to be equilibrium condition. So we have our net force equals 0 and our net torque equals 0. Right? That's where you have your three sets of equations, forces in the x, forces in the y, and the sum of your torques. When you have equilibrium met,
Torque.
you take physics in college, there is an entire year literally based around
Torque.
sum of your force equals 0, sum of your torques equals 0. No joke. It's awful. Statics. You are literally solving problems about things that aren't moving. It is the most unexciting class.
You took it?
Okay. It's after school.
It's after school.
Well, I mean, what? After 3:15, I don't care what you do with your phone.
Oh, really? Oh.
You want to take your phone out during this review session? Go ahead. Just don't be annoying and play music, or make a call and sit there and talk. All right.
Test something out quick.
So the important things about torque, I think really the big thing here is going to be equilibrium. When recognizing you have the sum of your forces equal to 0, the sum of your torques equals 0. And then really it just comes down to calculations, I would say.
It was hard though.
Yeah, I'm not saying it's easy. I'm just saying it comes down to equilibrium conditions and then just running numbers. And then after torque, our most recent unit was freaking hard. Fluids.
Just to let you know on the live stream, I can't see the board at all.
Yeah, I know. So you're kind of going to have to trust me. We had some issues with that the other day.
Did people watch you on the live stream the other
Yeah, I got some thumbs downs. What? What?
You were on to do it over Trovo.
Yeah.
Did you get any thumbs
My
up?
friend said that you would
Thumbs down on your video. Somehow she knew that.
Wait, You know who works there?
Yeah.
I thought I recognized that. She was kind of cleaning up one of the tables when I was complaining about my YouTube channel. Yeah, and I was like, and I was even thinking, I think that's a student. I don't have her, but I think she's a student. Okay, so yeah, that was. Oh, that's funny. Yeah. Oh, I had a really good pizza. It was fantastic.
Did you get any thumbs ups?
I think so I had gotten thumbs down, and I complained about it in class, and then so a student gave me a thumbs up after that. So I was like, hey, thanks, cool. And then a bunch of students subscribed to me and then unsubscribed. I mean, it's YouTube. I'm not doing this to like get likes and subscribes. I'm not a vlogger. My channel will stay unmonetized. You heard it here first.
Are you crying?
Okay.
Just so sad.
Wow. Okay. So, this being everything, I want you to take a minute or two, write down what you're going to want to go over.
You didn't write anything with fluids. You just wrote fluids.
I know, because we just did it.
So, it's still good to know.
You need to know everything out of the chapter we already did.
Fluids. We go over the back problems on the test today. That would be good. Then we know what we did wrong, and we were like, ooh.
I don't remember a thing
Alright.
about fluids, even though we just did it.
No one that wasn't here today, they'll get a different test, right? Because you said that if I had postponed my test, you would have given me a new one.
Yeah.
Yeah, you said that.
I did say that,
You
didn't
said
I?
that.
Yeah.
I didn't
We
hear.
can do that.
That'd be great.
I don't love it, but we'll do it.
Why do you not love it?
It's like McDonald's.
Okay, do you have what you want down from here? Because I want to erase this.
Yeah.
Okay. That was a lot of writing.
Can you just sum up fluids in like 5 words? Like the 5 main words. Pressure.
You gotta know about fluids.
What about
If you want it like legitimately summed up, Bernoulli's equation, continuity,
Continuity. I just said constituency.
pressure dependent on depth in a fluid, buoyancy, P equals F over A.
What is the C word again?
Continuity. The
The C word. That's not what I meant. I keep thinking constituency. and I don't
It's
know
not
why.
constituency. That's a politics term.
Yes, I know.
What about viscosity?
Viscosity, we don't really talk about viscosity. In fact, I think for even on the AP exam, it will specifically say, and I think it said this on the test today, ignore the effects of viscosity.
Yeah, I think it did.
What is that?
Yeah. It says the diver finds a rectangular aluminum plate. The density of aluminum is this much, and then it specifically says ignore the effects of
I
viscosity.
didn't do that properly.
Well, I didn't know there were effects of viscosity, so I didn't.
Well, we ignore them because it's like you do it in 5 years.
Are you gonna give like us points for ignoring the effects of viscosity?
No.
You get points.
Maybe if you like drew a picture of you ignoring the effects of viscosity, like giving it the cold shoulder or something. Like, I'm gonna ignore this viscosity here. Yes. Viscosity has to do with the rate at which a fluid flows.
When we did that lab where we saw if glue or water went faster, it was yeah. Because we got to
Can we do a projectile motion?
What?
Okay.
Do the one
Are we
on
able
the
to
test.
use old questions from the high school?
What do you mean?
Like,
I'm
did you
not
practice?
to work out
Okay.
there. Like,
If she gives you a question off of an old test, will you go over it with us?
I mean, if you want.
okay, go over the one from the test today first,
Yeah.
please.
The
Is
one
that how
on
you
that
want to
side.
start?
Yes.
Also,
I
I'm
would like
really
to not feel.
curious. I don't think anyone did the one with the spring. Did anyone do the one with the spring?
I had a couple
I
kids
did.
do the one with the spring.
Really.
I knew that one was harder.
Yeah.
It was
Uh,
harder?
You did that one?
Yeah?
How would you do that?
The thing, well, so if you don't know the equations, I think that one is easier because it's setting up a lab. But you have to know the concepts better. Whereas if you're familiar with the equations, but you don't know jack all about the concepts, you can probably muck your way through this back problem reasonably well.
I just didn't know. I saw the spring was that.
Oh, see, I thought the spring was super easy. Because
Yeah.
there's a problem out of the book that uses like the same idea.
Yeah, and I didn't understand that problem in the book. Also, the one with the vacuum cleaner that's like the diameter of the
You
vacuum
have the-
cleaner
yup.
is 2.5. How
Yup.
heavy of a brick can it carry?
Yup. Yeah, it's great. That's a good problem. You assume that the pressure, okay, so if something's a really good vacuum,
It's a zero pressure.
yes, you have a pressure zone inside that is zero. So you're going to, assuming that you have zero pressure inside, and then you can figure out the largest force downward that the zero pressure is able to like suck up.
Wait, so you can't suck harder than a zero pressure? All you can do is, this is like a really good, like it's just super strong. And it's like a centimeter diameter.
Yeah.
How would you do that?
Yeah, how would you figure that out?
And we want to find out how much you can lift, like what would
So you set pressure inside equal to zero,
Yeah.
and then you say, so the maximum pressure is going to be, you have, what, you have rho, P naught plus rho GH equals 1 atmosphere, and P naught is 0. So you're going to set rho GH equal to 1 atmosphere, and rho is going to be
Density of air.
basic, well, it's the density of the object you're picking up, and H, I'm trying to think, H you wind up using,
How do you figure
Oh,
out
no,
how much
that's
it
not
weighs
right.
then?
for that problem, gosh, I'll have to look back
And
at,
online, it doesn't help you. There's no one knows the answer anywhere.
that was 20,
20.
was it 20? I guess I don't remember off the top of my head.
It's 21 with the octopus suck thing.
Yeah.
It's just a really strong octopus. Like,
Oh, yeah.
you can't just be like, yeah, I can pick up this.
Okay, so the way you approach that one, yeah, I was using the wrong equation in my head right now.
Oh, also.
Oh.
We should do one at a time so we can actually get through full problems.
Continue.
So, with the vacuum cleaner one, like I said, inside we're going to assume it's a high vacuum pump, produces zero pressure inside the hose. The air below the brick will then exert a net upward force of P equals F over A. So F equals PA. You're going to set P equal to atmospheric pressure. A is going to be the area of your nozzle.
Isn't the brick bigger than the area of the nozzle?
Yes,
Because
but
it's
that
set
is
up
the
or-
maximum force upward
Okay.
that vacuum is going to produce,
Okay.
which means that's the maximum force of gravity that it can support from any size object. And you wind up getting like 65 newtons, right? 65 newtons, yeah. Yep, F equals PA, so P times the area of the hose, and then you're setting P equal to atmospheric pressure. Yeah. Okay, so that is one problem. Do we have another?
Could you go over, I know you went over it when we got the test back, but would you be able to go over the second short air-free response problem from the torque?
You're going to have to tell me what it is.
Here, I
Also, just a real quick question before we do that. If two people are pulling 100 newtons on both ends of the rope, what's the tension in the rope?
100 newtons.
Because
Because the tension in the string is going to be the same at all points.
Once the rope is like really strong, and the people are pulling really strong.
Oh yeah, I did whatever.
Like, if I'm pulling with 100 newtons, then what is the string immediately,
The wall is big,
let's just pretend that there's a curtain here, and there's a rope, and there's Mr. D pulling a rope, and he is pulling with 100 newtons.
And then the wall would pull back with 100 newtons.
There's no wall. This is a curtain. You have no idea what's going on over here. What is the tension in the string?
Is the string accelerating?
No,
100
nothing's
newtons.
moving. What's the tension in the string? 100 newtons. So then, the tension in the string is 100 newtons. What if I put another person over here, and they similarly have a curtain, and they're pulling with 100 newtons? What is the tension in the string? 100 newtons.
If the rope was connected to a wall or a person, it wouldn't matter because the wall would still be pulling with 100 newtons?
Yup. Yeah. Okay, so the what was it? The rotational dynamics test?
Yeah.
Did you put that up here? Okay. What was it?
The
2 on the free response.
Yeah.
So the pulley.
The one that I completely forgot.
Oh yeah, I did go over this. We'll go over it again.
Come on, Rachel.
Or is this a good problem to ask? If it's not, we
I
can do
remember
something else.
something about like the tension equals something, but I don't remember.
Tension, something, something.
I feel like that's all.
Number, math science,
Gravity.
math science I don't understand. More letters. I should do this with you. Letters with subscripts. 4 letters with subscripts.
All right. A pulley of radius r and rotational inertia I is mounted on an axle with negligible friction. A light cord passing over the pulley has 2 blocks of mass m. I labeled them 1, 2, 3 form, but they're all the same. So I can just say m1 equals m2 equals m3 equals m4. Assume that the cord does not slip on the pulley. Determine the answers to part A and B in terms of M, R, I, and fundamental constants. Okay, so we want to determine the tension T in the cord. To start with, we're just going to do a force statement, right? So I'm going to look at this. Again, this is getting at that same concept. The tension is going to be the same at all points. So what I saw a lot of students doing that hurt me inside was they solved for the tension here, they solved for the tension here, and added them up. Not how we do it. What are you doing?
Someone wrote a bad word on here.
Well, the only other person I've seen up at the board today was you earlier.
I'm a green marker. That was black.
Okay. So I have
Do that to me.
M1, or, I have 2M here. So I'm going to say I have a force of gravity down of 2 mg. I have a force of tension up. I don't necessarily know what that is. That's what I want to solve for. But if we're at rest, what's my force of tension?
0.
Yeah, well, it's 2 mg.
Yeah.
My force of tension and my force of gravity have to be equal here because I'm not moving. That's all you needed to do to determine T. So that's the first part. T equals 2 mg. I think that's the answer.
Well, you shouldn't look at my paper because I don't have any of the right answers.
I know. It's tough to remember the answers to old tests. Like, sorry. I'm doing my best
I
here.
remember all of them. That'd be fun. I remember all of them.
Well, naturally.
Last Saturday? I have it in here somewhere.
I don't remember what I ate for dinner 2 days ago.
Last Saturday, Ella.
I do.
Last night was I think
One block is now removed from the right.
I got that one right. Yes.
Now hung on the left. And we're going to accelerate downward with an acceleration of g over 3. Now we want to determine the following. So we're going to start out to part 1 and part 2.
Did they give us the acceleration of g over 3?
What?
Did they give us the acceleration?
Yes, that's given.
Oh, okay.
So now we are basically going to do the exact same thing, except now we're going to set sum of our forces equals ma. So I want the tension on I want this tension, and I want this tension after the block has been moved. So, what's my force downward? 3 mg. My force upward, I'm just going to call Ft. And my total mass is 3m. And my acceleration is g over 3. So I'm going to have Ft plus negative 3mg equals 3m times g over 3.
And is the force of tension the same as it was before, or no?
No. Because now we're stuttering. Now we're asked to solve for the new tensions on either side. Now, I originally had this 2 mg. That was the same in all points along the string. Now I've moved a mass from the left, or from the right to the left, and I want to determine the new tension on this side and the new tension on this side. Yeah.
So, if the pulley is moving, that means that the tension is not equal.
If the pulley is moving and the pulley is not assumed to be massless. So now that we have a pulley with a moment of inertia, which means it has mass, there's going to be different tensions. And you can get that just by following through with Newton's laws. You might not believe it right now, but I mean, if an AP problem is going to ask you to determine tension 3 on the left, tension 1 on the right, just trust them and do it. And maybe you get tensions being the same on both sides, but maybe you don't. So here you get 3 mg over 3.
How can you have it when it's not the same all?
Because you can treat this pulley as if it were an additional mass. And so like there's gonna require, there is a required tension to move this pulley, and it's going to be greater in the direction that the pulley is moving. Just like there needs to be like a net force to get something moving, there needs to be a net torque from these two tensions to get the pulley to move. I think that's probably the best way to think of it. So we have here Ft plus negative 3 mg equals mg. So what plus negative 3 mg is going to give you mg? Move 3 mg over to this side. Or no, I'm sorry. Negative 3 mg, yeah, negative 3 mg comes over to this side. We're going to have a force of tension of 4 mg.
And then you have to do that for the right side too.
And then you do the same thing for the right side. You're going to apply Newton's second law. Sum of your forces is equal to mass times acceleration. Now, the tension may not be the same, but the acceleration here is going to be the same. So we're going to say the sum of our forces here is going to be mg down, and force of tension up. We are going to say force tension plus negative mg equals, our m on this side is just m, and our a is g over 3. So I'll add mg to both sides. I'm going to get force tension equals mg over 3 plus mg. It's going to give us a total here of 4/3 mg. So then for part 3, this is the meat and potatoes of this problem. This is going to require some work with torques. So now we need to convert these tensions into torques. And we're going to start with the sum of our torques equals I alpha. And we know that alpha equals A over R. Now we want to solve for I. So we are going to start Well, if alpha equals A over R, I know my A is G over 3. Over R, which is the same as GR over 3. That is going to be my value for alpha that I plug into the sum of my torques equals I alpha. I'm going to get my torques from my force statements. I'm going to have a torque, I'm going to have a torque out of the page and a torque into the page. I'm going to have a counterclockwise torque and a clockwise torque. And that comes from my two tensions. So I know torque equals FD. So I'm going to have my torque on the left being 4 mg times R. And I know that on the right side, my force is 4/3 mg. Similarly, my distance is R. So I have 4 mgr and 4/3 mgr.
GR over 3 would be G over 3.
Well, so if I have G over 3 over R, that's like G over 3 over R, which is G over 3 times
The inverse of R, so 1 over R.
Yeah, and then so you get, wait, yeah.
No, it's G over 3R. Because if you divide 1/4 by 2, you get 1/8, not 1/2.
G over 3 over R. So that's like,
It's like G over 3 divided by R over 1, and then you multiply by 1 over R. So then you multiply the numerators and then you multiply the denominators.
am I just thinking about that wrong then? So you're saying it's G over 3R? That might be right. I guess maybe I'm going through this a little too quick. Not having the answer key right next to me is making me slog through this myself. So I'm dividing by R, which is the same as multiplying by 1 over R. Yeah. So I would have G over 3R. And that is my alpha term. So instead of GR over 3, it should be G over 3R. So that's all that changes there.
So I got the sum of the torques equals I times G over 3R, but what's that under? Like,
Where?
is that right under that? The
This?
tau equals FD?
Yeah. This, I'm solving for each of my torques.
Okay.
And I get my torque from FD cosine theta. I don't need to worry about theta here because I'm always perpendicular to my radius. So I have 4 mgr and 4/3 mgr as my two torques. So my net torque is going to be 4 minus 4/3, 12/3 minus 4/3, 8/3 mgr. So my net torque being 8 over 3 mgr equals I times alpha, which is G over 3r. I'll divide both sides by G over 3r. And that'll give me my, I can cross G off on both sides to start with. If I multiply by 3r, then I'm going to get 8 over 3 times 3 m r times r equals I. So these 3's are going to cancel. I'm left with 8 mr squared equals I, and I don't think that's right. I think the answer is 2 mr squared. Am I making a mistake with my math?
Did that also adding the 4 MGR and the 4 times MGR? Is that
The only thing I can... Well, I might have the key back here, so I'll see if I'm screwing something up, but I shouldn't be. I hope not.
Is it 8 MR squared? That's what he got, but that's not right.
Yeah, yep, the answer is 2mr squared, and I'm thinking that this is wrong. Because we have a 3mg down plus T3 equals 3m times g over 3. Yeah, I'm not very smart. This g over 3 should be negative, right? Because if we're saying mg is down, then g over 3 should also be down. So our force tension instead of 4mg should be 2mg. Changing this to 2mg is going to be what? You'll have 6 over 3, 4 over 3, subtract those, you'll get 2. So you'll be left with 2mr squared. Does that make sense? I can go through the math if you need me to, but if that makes sense, that's where our mistake was.
So the sum of the torques is on the left side 2mg instead of 4mg?
Yes, and that comes from the fact that our force tension, I did not have g over 3 be negative. One little mistake really screws stuff up. So that's that one. That is a big problem for sure.
And then can you do the one from the end of test today?
Yeah, we'll go through that. You want your test back?
Here.
I mean, it is yours. Okay, the test today. Let's see what we got. Is this cool if I erase it, or are people still writing? I'll give you a sec. So I'll just talk about the problem from today then, and I'll get it written up here as soon as I can. So we've got a diver descending from a salvage ship to the ocean floor at a depth of 35. Density of ocean water is 1.0225 times 10 to the third kilograms per meter cubed. We want to calculate our gauge pressure and our absolute pressure. Like I said, the only difference is that absolute pressure, like your answer for B is going to be the same answer plus 1 times 10 to the fifth. Finding the rectangular aluminum plate, it gives you the dimensions. You're going to use that to calculate your volume. You're going to use the density of aluminum to determine the mass. And then, I guess you don't really need to do that, but I would, because then you can find your force of gravity. Yeah, you want to find your force of gravity down, and you want to find your buoyant force up. And then, so you're going to have part C, your tension. Again, that's going to come pretty much straight from Newton's second law. So you're going to be looking at your force diagram, which I'll get up here in just a sec. And then the only thing from D, you don't actually need to calculate the tension. It's just asking you if the tension is going to increase, decrease, or remain the same if we start accelerating upward. The tension? Tension's going to increase. Yes. Because if you're accelerating upward, then you have to... You're basically going to have this additional force term upward from the acceleration of the cable. Yeah. And I'll go through this. Are people done with this? Can I erase it now? Okay.
Yes.
If you're doing buoyancy, you're doing PVG, is it the density of the fluid?
Rho VG.
Sorry. It's the density of the fluid, not the density of the object.
Yes.
The density is always of the fluid, right?
Yes. That's why that second problem on the test today, where you have a box and you fill it with different stuff, doesn't change your buoyant force at all. Your buoyant force is just dependent on the volume of the object, but the buoyant force changes based on the density of your fluid.
I got that one.
I think a lot of students got that one wrong.
I was debating on that one.
I put it in with air.
I tried to find a good balance of the multiple choice where it was like they were easy, but like you had to know, like you gotta know. I'm
It's not easy.
well, I don't like doing those things like, you know, here's something we barely touched on at all. Do you remember this obscure fact that's like one sentence out of the book?
But just like, okay, so the question number 2, like, it was a little bit like you were trying to make us not think that the right answer was the right answer, you know?
By saying the correct answer was none of the above when really it's all of the above, like trial 1, 2, and 3, like they're all the same.
Yeah, I don't know, but the wording on that, I thought that like,
Wouldn't the buoyant force depend upon how hard the box is pushed in, because then it will displace more water?
Well, once it's all the way underwater, right? It says it's submerged, so we can assume that that's completely submerged, which is after that it doesn't matter anymore.
So it was none.
It was none of the above because it was all 3 trials. The buoyant force is the same.
I was like, oh.
I will never go with none of the above on a test.
It's
All of the above, that's okay. None of the above.
AP loves none of the above. You know what I hate that the AP board loves? They love giving you a bunch of statements.
Oh yeah,
I
and
hate
then 1,
those.
2, 1, 3,
Oh, yeah.
1, 2, and 3.
I
just
hate
3.
that because it's
Yeah, and then like A will be 1 and 2, B will be 1 and 3, C will be only 3. Oh, I hate that. It requires you to really know what's going on, but I mean, it's so easy to slip up. Anyways, did we want to go over the last problem?
No, I think that's good.
Okay.
Yeah, it's gonna be good. Should we go over the one with the spring?
Out of the book,
The one
37.
I don't know how to do it, but like also it might just.
Oh, the other one on the test?
Yeah.
You want to talk about it?
Could you like explain it?
Yeah, I can. So on this one, now this is more like wanting to experimentally determine something. And the AP board has a problem like this on every AP test, for physics at least. I'm assuming some of the other sciences are the same, but there is always an experimental design problem. So, you know, if you take the AP test, the content, you know, the subject of that question is, of course, going to change every year. But the ideas are going to give you something where they're like, hey, here's a thing. How would we do this experimentally? So in this case, we have a cylindrical beaker containing a fluid, and we need to determine the density of the fluid. So we have a beaker filled up to about there. And then I have a ring stand with, you know, this funky object on the end of a spring.
Spring's hanging down?
What?
Is the spring hanging down? From the
Yes.
stand?
This is just, we need rho of fluid. So we want to calculate the density of the fluid. On a regularly shaped object of known mass m, so our m is known, and its density is way higher than rho. So that basically means that there was one student actually who asked me about this after class, and he said, well, what I said was you drop the object, time how long it takes to sink to the bottom, and then you can find its acceleration through the fluid. I said, you can't really do that because since our object is so much denser than the fluid, it's just going to fall immediately. It would be like dropping a rock in, 6 inches of water. It's going to be impossible to time that. So you can't do it that way. It does not have to do with dropping your object into the fluid and timing it. Especially because it starts out, we want to determine the spring constant K. We're allowed to use a ruler, a stopwatch, and string. So really all we need here is our ruler. And what we're going to do is I'm going to, remove the beaker. I'm going to determine the elongation of my spring with the mass on it. I'm going to put it in the fluid, determine the elongation of the spring with it now in the fluid. I know the mass of this object, and I'm also going to be able to determine its volume quite easily by determining how much water it displaces. If I know the volume of water it displaces, I know its buoyant force. If I now have a force, the only difference between this being in and out of this fluid is that in one situation I have a buoyant force. That means I have a force. I can use F equals Kx. Is there a question?
So if the spring is half underwater and half above water, since the water would have a force up, so the spring would be tighter. Would it be tighter in the water and looser out of the water, or would it be the same amount of tightness?
I'm not entirely. So I hope this is how you're asking it. The water is not going to have any effect on the spring because I think it says that our spring has negligible mass, so there's not going to be a buoyant force on the spring itself.
Okay.
The spring.
So the spring will be equally stretched in the
yes, regardless if it's in the fluid or out of the fluid.
Okay.
The only difference being the object on the end. There will be a buoyant force upward when that object is submerged. And so you're going to be looking at this as our buoyant force is equal to Kx. You know your elongation. You're able to calculate your buoyant force from rho Vg, knowing that rho V is the mass of your object, and you can go from there. Find your spring constant. That's all you have to do there. For the second part, we have a spring object system, so that the object is immersed in the unknown fluid. Describe any changes that are observed in the spring object system and explain why they occur. Oh, you know what's even easier than this? You don't even need to do this part. You can just remove this, take your object off, put your object on. You know its mass, so you can say F of mg equals minus Kx. That makes it even easier. Then you don't need to worry about the buoyant force the object experiences at all.
Okay.
Yeah. So now we're going to immerse the spring in the fluid, describe any changes in the spring object system and explain why they occur. The only change is going to be that our spring is going to be less extended due to the addition of a buoyant force from being immersed in a fluid. So with the addition of a buoyant force upward, that's going to reduce our net force down, which is going to reduce the elongation of the spring. That's the only thing there for for B. For C, explaining how we could experimentally determine the density of the fluid, that's where we do this. We already know our spring constant. We're going to be able to determine that our buoyant force is equal to minus Kx. Same process I described there. And then D, it says, show explicitly using equations how you will use your measurements to calculate the fluid density rho. So you'll basically walk through this, everything I talked about. You'll say FV equals rho VG. And you'll set that equal to minus kx. And then what it wants you to, this is pretty much all you would do. You might write it out in sentence form. And that's how you would do the last part. It gives you this huge table with symbol and physical quantity. But you start here and move to there. Any other questions? You guys don't want to stick around? It is getting late.
What do we need to all have for our foot thingy that we can turn in?
What do you need to know for it, or what do you need to do for it?
Include?
So on the very first page of the packet,
I don't have
there's. Oh, I guess you had to turn it in, right?
Yeah. I had my foot. I did some stuff. I don't remember what that means.
That's a good start.
I don't remember what it means, though. That's a while.
So this front page, under pressure activity. So there's a couple things on there that I had to nix, of course, because we're not doing a Google sheet together. That was what they did last year, and I felt like I know that some people are a little sensitive about their weight, and I didn't want to have people report answers if they didn't want to, so I'm just nixing that entirely. Other than that, it says there are some questions you need to answer. So like number 1, it says, what is the physical definition of pressure? You need to answer that. Number 2, in what metric units does one measure pressure? You got to answer that. Check that your answer is equivalent to pascals.
Can I see if I answered it in my packet? Is that mine?
No, this is just a blank one. You want me to find your packet? Oh my gosh. Okay. Right over here.
Don't forget about me, okay? Me? Oh, I won't. Oh, I see. Check. No, it's right there.
I did not get a packet from you.
Bye, Mr. Dielentheis.
Have a lovely evening.
Of course.
Prestone, Eric, Nate, Jackson, Zach, Powell, Kyle, Robbie, Austin, Jack, Noah, Evan, Noah.
It's right there.
Oh, yours got stuck. Okay. Okay, so you'll need to get that campy down. I have that graded, so you can take it.
Oh, okay.
I don't need it.
Is this good, or do I need other stuff?
Well, you'll need to,
Put it on here.
yeah. You can just put it on the back.
Okay.
Just make sure you're answering all those questions.
So for the graph, does it need to be off foot or?
Yep, it needs to be your own foot.
Oh.
The idea was I want you to use, like your own shoes, your own weight, so that you're calculating like your actual pressure that you're exerting on the ground as opposed to, someone else's in your group. Yeah.
Alright. And in the book, like there's like an object submerged, right?
Mm-hmm.
And there's like Boeing force and there's FG, but there's like another one that's like T of like air and T of water. Like, what is it?
Where? You're talking about.
There's some
Our T vector here.
Excuse me? Crazy.
Oh, that's just our tension.
So heavy, it's like upside down.
Our tension due to the strain. So it's just saying that in air, our tension is going to be different than our tension in the water. Because our tensions are going to change based on how much, how much force down we have. Like how much net force down we have. Because when we have a buoyant force, right, see how they have it here? Our tension in the water is less because we have the addition of a buoyant force. That's all it was saying there. Yeah.
Thanks.
Yeah, no problem.
See ya.
Yeah, have a good one. All right, I think that is that's it for the stream. We never had anyone tune in. All right, so that's all she wrote. We are getting out of here.